Okay, we've seen that molecules are moving at an enormous speed. But how far can they get before they hit something else? Are collisions all the time, or can a molecule make it halfway across the room between collisions? Well, to work it out, let's try an approximation that's actually very widely used in physics, and indeed in fields outside of physics. It was used in World War II to calculate the probability of bombers colliding, for example. The idea is that we're going to just consider one molecule as moving, and every other one is just sitting there. I'm just going to ignore the motion of the other ones. This is probably not a bad approximation because the motion of the other ones might carry them into the path of our molecule or out of it, and probably there's about an equal chance of either, so probably it's not too far bad. So anyway, we've got our single molecule and it's going along. Now what does it mean for it to hit something? Now if it was a billiard ball, that would be quite straightforward. If the centres passed within twice the radius of each ball, then they would touch. But molecules are fuzzy and not circular, so it's not quite so clear. So let's just for the moment call it R. If they come within some distance R, they're going to bump. And now we can imagine in a time t that our molecule sweeps out a cylinder. Radius, this R up here, length, velocity times time. And the number of molecules it collides with will be the number whose centres are inside this volume. So how many is that going to be? Well, we're going to have a number per unit volume n times the volume, which is Vt times pi r squared. So pi r squared is the area of the end here times the length. That gives you the volume multiplied by n, which is the number of molecules per unit volume. So that's how many other molecules are going to have their centres somewhere within the cylinder. So that's how many it will collide with if it moved in a straight line over the entire time. Now we'd expect a collision to happen when that number comes out to be about 1. So when there's one molecule in that cylinder, you're expecting a collision. So the average length the molecule goes between collisions, L, which is going to be equal to Vt, is just going to be 1 over pi r squared n. Now we can work out n from the density of air, about a kilogram per cubic meter, divided by the mass of one molecule, which we've worked out before. And so n comes out to be about 2 by 10 to the 25 molecules per cubic meter in air at sea level. But what is the effect of R of an air molecule? How close does it have to get? Well, the trouble with air molecules is they're diatomic. But let's assume we've got two molecules and each of them has the two atoms in a molecule, and each of them has a radius about 10 to the minus 10 meters that you worked out earlier as a typical size of an atom. So the overall molecule, if they're just touching, is about 4 by 10 to the 10 this way and about 2 by 10 to the 10 that way. That's assuming they're going side on. They might of course be going this direction rather than that way, but it's probably not going to be too far wrong. So if we average 4 by 10 and 2 by 10 to the minus 10, we can treat it more or less as a circle of radius about 3 by 10 to the minus 10 meters. And that should give us about the right cross-sectional area for a collision. Now that's roughly the size of one molecule, and so if another molecule comes within about 6 by 10 to the minus 10 of a meter, there should be a collision, roughly speaking. I mean, maybe the two of them will go past like this, but maybe they won't. It's probably not going to be too far wrong. So if we plug all this into our above equation, up here, we get a length which turns out to be about 44 nanometers. So it's about 44 by 10 to the minus 9 meters, which is actually about right. The real mean free path in air is actually about 68 nanometers, so within a 50% of our crude estimation. So what this means is that molecules don't get very far before colliding with another one. What's the typical time? Well, the typical time is just going to be this divided by the typical velocity, which we've already worked out. And that turns out to be about 0.1 nanoseconds. So that means 10 to the minus 10 of a second. So collisions are incredibly frequent. You've got 10 billion collisions per second. This is not sounding good for nanotechnology. A constant rain of fast collisions on any atom, and they don't get very far between collisions. Now this distance, 68 nanometers or 44, is actually pretty small, but it's a lot bigger than the size of the molecules, which is less than a nanometer. So what this is telling us is that from a molecule's point of view, air is mostly empty space. If we think of each molecule as being the size of a golf ball, they're separated on average by about a couple of meters, the size of a person. So air is mostly empty space, which is why the molecules can get many, many times their own length between collisions. But still, collisions are very frequent and very fast.